we continue our data fest. And our next speaker is Erik Harutyunyan from SuperAnnotate. He's a machine learning engineer at SuperAnnotate. And he's going to talk about, the topic of the talk is speeding up counter detection networks using channel pruning and knowledge distillation. I think Erik can take up from here. Erik, do you hear me?
Yeah, okay. Let me share the screen.
Yeah, you can share the screen and start.
Okay, hello everyone. I'm Erik Harutyunyan, computer vision engineer at SuperAnnotate. And today we're going to talk about how to speed up specifically counter detection networks with the use of channel pruning and knowledge distillation methods. And in our agenda today, I've prepared these parts, which I will talk next briefly. So first of all, we'll speak about counter detection using deep learning, and I'll introduce the general architecture approaches and also the current architecture of the state-of-the-art model. And next, we are going to talk about a little bit about channel pruning approach and what results I've got doing my experiments of speeding up counter detection networks using channel pruning. And next, I'll finally introduce knowledge distillation approaches and results of the experiments too. And I'll mainly talk about Hinton's approach of knowledge distillation and also backbone knowledge transfer approach. So let's start from introducing the counter detection networks. So as you can see, I've brought some high-level abstract representation of the very first model of deep learning based approach of predicting contours of objects present in an image. As you can see, generally in this type of networks, we utilize some familiar backbone network, for example, VGG16, but we only use the convolution parts of these networks as a backbone. For example, in VGG16, only 13 convolution layers are present, and the rest are fully connected layers, which we drop during this task because we don't need any fully convolutional layer here. And we are going to, when given an input image, we are going to predict this kind of probability map where on the boundary pixels of an object, we must have higher probability, and on the other pixels, which are not a boundary between two objects, we must have ideally 0 or very low probability. So our final output of these models has the same size as the input image, and for each pixel we are predicting the probability of whether that pixel is a boundary or not. And these deep learning based counter detection networks are generally following this convention of having some familiar backbone network, as I said, like VGG or ResNet, and they attach some a sequence of convolutions to each block of this backbone network, which from these feature maps get this side output probability maps, as you can see here. So for an input image of these two horses, we have here 5 side outputs in this holistically nested edge detection network, so which is the very first counter detection network that was presented in 2015. We have these 5, we usually get these 5 side output probability maps, which you can see here. And in shallow layers, we usually get all possible edges present in the image, and it's very similar to general edge detection, which captures any change of color in the image. And as we go deeper in the model, like in a very deeper layers that have a much bigger receptive field, we capture the general, we capture also the object semantics, I would say. So we don't have these tiny edges that are present in shallower layers, but we have more general boundary-like edges in more deeper layers. And when we have these several side outputs, the final output usually learns through a single convolutional layer with one kernel, learns some sort of linear combination of this side output probability map, which is called the fusing layer. So it learns which probability map must contribute more to the final prediction map of our network, and this is called the fusing, and it gets the final output of our model, the final prediction map, which we'll need to get for an image. And so after this very first network, the general approach hasn't changed much, and even the most recent networks like this one, the bidirectional cascade network, it also employs this kind of strategy. It takes these red blocks, as you can see, it's the VGG convolutional layers. So it's the same VGG convolutional layers with batch normalization. And some logs of sequential convolutions, which are after which we get the side outputs of the model is, for example, in the bidirectional cascade net, we have 10 side outputs on the on this CEM blocks, which stands for scale enhancement modules. It's some sort of convolution by each other, so dictate very meticulously the gesture in these CEM modules, but we don't have any type of architecture. I'm going to also speak about the dataset on which I'll show my results and the scoring evaluation metric that is used to qualitatively compare the results of the several models, and by which we will decide whether we got good good performance when the model is sped up by several times. So in our dataset, the dataset is called BSDS 500, in which we have 200 train images, 100 validation, and 200 test images. And so, as you can see, the dataset is not so big, and training this counter detection, during training these counter detection models, we employ a lot of data augmentations, such as scaling the images 1.5 times or 0.5 times, and rotating and etc., like flipping, and these kind of augmentations, employing which we usually get around 30,000 images in our training set. And for the evaluation metric, we employ ODS F1 score. So the most unfamiliar part from this, it could be the ODS part, which stands for optimal dataset scale. This means that it computes F score for a given threshold employed for all our 200 test images, which is the following. As I said before, the output of our prediction model is a prediction map in the pixel, and each pixel is a probability and has a value from 0 to 1. And so we must threshold these images to get a binary image where border pixels, boundary pixels must have a value of 1 exactly, and the pixels that are not a boundary will have exactly the value of 0. And so during this, when computing this ODS F1 measure, we must threshold all images with the same number. For example, if this optimal dataset scale, like the threshold is 0.3, then every image in this test set is thresholded by the value of 0.3, which means pixels that have probability bigger than 0.3 are assigned to class 1, like the boundary, like they are considered to be boundaries, and pixels that have probability less than 0.3 are considered not boundary and have the class 0. And after that step, the usual F1 measure is computed, which I think is familiar to you. And also, let me briefly introduce also the state-of-the-art model in the counter detection, which we will use in our experiments, and which we want to speed up without losing much accuracy in ODS F1 measure. And so, as you can see, it again has the familiar VGG 16 convolutions as its backbone. And this right-hand side, as I said, are some architecture of like combination of some convolutions which lead to side outputs. So we have 5 side outputs, and as I said in a holistically nested edges slide, these side outputs are then concatenated and followed by one-on-one convolution, which basically learns a linear combination of these side outputs and gives us the final output, which we'll need to compute this ODS F1 measure. So, as I said, as you can see, these state-of-the-art models and also the other ones are very heavy, and they also usually employ, besides VGG 16 backbone, ResNet 101, which is significantly heavier. And so, as you can guess, they are very slow to work on demand, even on GPU. And besides, even if we decide to use them on GPU, that will lead to high costs of GPU usage on cloud compared if we could achieve the same performance much faster and be able to run it on the CPU. So that's why to minimize the costs of GPU usage and even speed up the models to work on demand, we conducted this research and tried to speed up these models. And as I said before, on dataset slides, I showed the original images of present in the dataset, and here on each experiment, besides reporting the ODS F1 measure, I'll also present visually the prediction for that exact same images, which you can visually use to on which you can visually also see whether the performance is good or bad, and whether it improved or not. And so this is the result of the state-of-the-art model. And so it has an ODS F1 measure of 0.811. And let's also talk about the approaches that I employed to compress and speed up these models. And so first of all, we'll talk about channel pruning, which is going to decide the optimal number, I would say the optimal number of channels in each block of convolution, and remove the other filters that are present there. And in comparison or in contrast, the knowledge distillation is is not pruning anything from the model. It just takes as an input a very cumbersome model like deep and with very high performance, and also a more lightweight and faster model, and tries to improve the performance of the lightweight model by using the capabilities of the significantly heavier model. And so to talk about channel pruning, let's do this. It has generally two steps, and channel pruning methods are usually employed on networks which are already fully trained. And after this training step, these channel pruning algorithms are employed to sequentially go into each layer and prune the most unimportant filters in each convolutional layer. And so it has these two steps which are performed iteratively. The first step is channel selection. And for each layer, as we go sequentially in our model, we'll decide which channels to drop and which to keep. And there are several approaches for this task. Some approaches employ lasso regression, and they assign coefficients for each channel. And by employing lasso regression, we get the coefficients. So the coefficients which are not zero on the end of lasso regression, that corresponding channels are kept. The other ones are dropped. And also there is another approach with reinforcement learning. And this is a more recent one, and it's more computationally heavy because it has a learning agent that is ran for several hundred iterations, and it decides on each iteration what percent of channels in each layer to keep and what percent to drop. And after this channel selection and pruning step is performed, there is a reconstruction step which is employed again on each layer sequentially, and it uses the input of this layer and the output feature map of the original layer. So it tries to update the weights of this layer. So the weights are pruned already, and it tries to get the same feature map with this layer by using lesser number of inputs, lesser number of filters than before, because the other parts were pruned. And this reconstruction step is usually done using linear least squares. So for a given layer, we take input feature map and the original output feature map that this layer had before employing channel pruning, and we try to optimize these new weights, new filters that are already pruned to get very close output feature maps than we had before the pruning step. And by employing this channel pruning approach on our model, we got 0.726 ODS F1 score. So as you can see, the performance dropped significantly, although the network was sped up nearly 2 times. And so I decided to proceed with by trying knowledge distillation approach for achieving this goal. And in knowledge distillation, we have 2 models generally, teacher and student. As I said, the teacher model is the cumbersome one with high accuracy, and student model is a lightweight and is significantly faster. And during training, the output of the feature model or of the teacher model, the outputs are used for the supervision of the student model together with the ground truth. And in some cases, the feature maps of the middle layers of the teacher model are also used for supervision of the student model, and about which I'll talk a little bit later. And for the student models, we employ these 2 ones. So it is similar to architecturally to the state-of-the-art model, and what we changed was the backbone, which is the lightweight MobileNet V2 backbone compared to VGG16 or ResNet. And the results of a student model without even employing some knowledge distillation is 0.76, which is even higher without even employing knowledge distillation, and it's generally higher than channel pruning approach. And so let's talk for the very first part about the Hinton's approach, which uses the outputs of the teacher model to supervise the student model. And as you can see, for the loss formulation, we have the general loss function, which we use to train with ground truth labels. And we also add a loss function between the outputs of teacher model and outputs of student model, which is called soft labels and soft predictions. And for our training models, we employ the mean squared error loss function between side outputs and final output of teacher layer and corresponding outputs of student layers. And so the ODS improved to 0.7 775 after this, and as you can see from the images, they also improved and got significantly better. And let's also briefly talk about our final approach, which is backbone knowledge transfer. And this approach, besides having these two loss functions between outputs of teacher model and student model, and the loss function between outputs of student model and ground truth, we also add a loss function between backbone, the final convolution layers of our backbone models. As you can see in our state-of-the-art teacher model, we have this final convolution layer, and for the mobile net part, we had this one, and we employ a fully connected layer to bring them to the same dimension. And after that, we compute a mean squared error loss function between these, and we add this mean squared error loss function to our general total loss function with some coefficient lambda. And after this, we also improved our ODSF measure to 0.789, and this final improvement got very close to the state-of-the-art performance. So it is 2% less than the state-of-the-art performance. And as you can see, the images are also very well, are very good ones. So we generally predicted very well the boundary edges, and didn't predict or predicted with low probability the redundant edges. And the final, I brought the final table of the ODS scores of the models and methods I presented today. And besides that, I also reported the CPU time of these models that are run on the same CPU, and also the memory usage and number of parameters each model has. And as you can see, the student model with the backbone knowledge transfer has very close F1 score to the state-of-the-art, and is nearly 5 to 6 times faster than the state-of-the-art network, and has significantly less parameters than the state-of-the-art network. So thank you very much for your attention.
Thank you, Erik. We have a very short time till the next talk. So I guess I'd like to ask one most probably short question, and then we'll go to the next talk. The question is, as I understood, the knowledge distillation is not only producing much higher results than the pruning approach, but also it's much faster, and also the number of parameters were a lot less. So as I understood, if you have a problem of, or if you have a goal of getting a lightweight model, would you rather not jump straight to a knowledge distillation approach without not even trying the pruning one?
Yeah, so from my experience, I'll do that, because from the papers and also from the experiments, channel pruning approach usually performs very well on feed-forward networks, and in this kind of complex tasks, like the ones that are not usual classification tasks, we don't have feed-forward networks, and networks are more branched out and even have some residual connections, in which case these channel pruning approaches perform poorly. And so also, yeah, I will definitely jump to the knowledge distillation method rather than trying channel pruning.
Okay, I guess I'll try to ask the question in the chat as well, because it seems very interesting, and if you can please answer this one briefly. So the question by Levan is, do you use quantization, and is quantization worth to apply after knowledge distillation or
so I've tried to use quantization, although not very much. So the problem with quantization in my experiments were during this task that it generally doesn't converge well. And if we restrict the bits of our weight parameters like they do in quantization, the convergence becomes very poor, and the network starts to diverge very frequently, and it's harder to optimize these kind of networks. That's why I didn't perform very much experiments on this quantization part.
Okay, thanks a lot, Erik.
Thank you.
Let's move forward with the next talk. And the next talk is by Shantanu Sarjan from Pixar. He's a senior machine learning researcher at Pixar and team lead there. And Erik, do you hear me?
Yeah.
You can share your screen and start your talk.
I suppose Harutyunyan will mean Shant, not Erik.
Sorry, Shant. Yeah.
Okay, now I will share.